All right, everyone. So we're going to be talking about Lab 1 and maybe the conclusions you might have come to and, what Lab 1 is about in general. And so in Lab 1, you put objects in water and you looked at the buoyant force on them. Okay? And so the main point of Lab 1 was to learn about Archimedes' principle and buoyant force. So what Archimedes' principle says is that when you put an object in water, the water pushes up on the object with as much weight as the weight of the water that was displaced. So really what that means is that if you put an object in water and you're pushing away, like this object has to push water out of the way when you put it in there. If you push away like 10 newtons of water, then the water is going to push up on the object with 10 newtons of force. Okay? So however much water you push out of the way, the water is going to push back up on the object with the same force as the weight of that water. Okay? And then the lab goes in to explain where how to calculate the buoyant force, right? So the important thing to understand here is where buoyancy comes from. So when you have like a body of water and even if there's no object in it, like the water that's deeper down is going to experience the weight of all the water above it. Okay? So what that means is that like water at the surface, like obviously it experiences gravitational force just from the earth, but like it also experiences the weight of like the water above it, but there's not that much water above it, so it doesn't experience much extra weight above it. But as you go deeper down, the water is going to experience the weight of it's always going to experience the weight of the water above it, but the weight of the water above it is going to increase. And so what that means is that as you go deeper into the ocean, the water has a higher pressure. So if you've ever swam, in like a pool or in the ocean, as you go deeper, you feel a lot more pressure around you, and that's because you have a bunch of water above you pushing down on you, right? And we know that if we have, or maybe we don't know it, but we can figure it out that if I have some pressure here and some pressure here, if pressure 2 is greater than pressure 1, then there's going to be a net force upwards. And so that's what's happening here. So the pressure is deeper in the water, the pressure is higher deeper in the water. So when you put an object in water, the pressure is always going to be higher on the bottom than on the top. And what that means is that there's going to be a net force upwards. Okay? And so the equation for that is rho fluid times g times v displaced. So the density of the fluid times the gravitational constant 9.8 or 9.81 times the volume of the water that was displaced. And so what this means is that the buoyant force for any object, it doesn't really matter what the object looks like. It only matters how much volume you're displacing. And I guess whatever fluid you're putting it in. But let's assume we're putting it in water. Then all we care about is the amount of water that we've displaced. Okay? So your experimental apparatus had a force sensor, and then you hung weights from it. Okay, and you dipped them into this water here. And then you looked at the data that the force sensor gave you. All right. And so then we actually got into the actual lab, right? So you drew 4 separate force diagrams for the object. So like A, you had an object hanging from a force sensor above water. So our force diagram is just going to be mg down with tension up, and they're balanced. And then in 2, we had the force sensor hanging from the force sensor fully submerged in the water. So if it's fully submerged, then obviously I still have mg and I still have tension, but I also have a buoyant force. And the buoyant force could be greater than the tension, or it can't be greater than the tension, because tension. Sorry, yeah, I'm trying to say it cannot be greater than the tension, because tension plus the sorry, never mind. I'm lying. It can be greater than the tension. The buoyant force can be greater than or less than the tension, but the two of them have to sum up to be 0. So essentially, like FB plus tension minus mg has to be equal to 0. Okay, and for C, where the object is hanging from the force sensor partially submerged in the water, the free body diagram looks the same. But so it should be straight down. The free body diagram is essentially the same, but now the buoyant force is lesser than in part B. So I'm going to make it a little bit smaller compared to the tension. And then in D, it kind of depends how you interpret it. If you'd interpret it as like, actually, either way, the force diagram looks the same, but you can interpret the object floating on the surface of water as if like you have some body of water here, and then an object is like literally floating on the surface and not pressing into the surface at all due to surface tension. But I think how you should interpret this is like you have a body of water, and then an object is like just floating, partially submerged, but there's no more tension because now the string is like slack because the object is fully supported by the buoyant force and doesn't need the string to hold it up. So if that's the case, then you only have a buoyant force and mg, and again they're balanced. Okay. So 1.2 says to write the Newton's second law equations for each of them. So for case A, where we're just hanging, we have the tension up and then mg down, and those have to be equal to 0. Because the Newton's second law equation is just the sum over all forces equals ma, but our objects aren't accelerating anymore, so we have m times 0 here, which is just equal to 0. And for B, we actually already wrote it, but for the object that's fully submerged, we have tension plus the buoyant force minus mg equals 0. For C, we have the same thing. And then for D, we have just the buoyant force minus mg equals 0. Okay? And then 1.3 says to essentially show this equation's true. So this equation is actually only true when your object is when your object's density is less than that of water. Because if your object has a greater density than the density of water, or whatever fluid you're putting it in, then, let's say it was double the density, then you could have 200% of the object submerged, which obviously doesn't make sense, right? So getting this equation is actually not as complicated as it sounds, I think. So if we have the mass of the object or the volume of the object divided by the mass of the fluid, I'm going to write water, over the volume of the fluid. And I've replaced these here because I'm just taking this rho equals mv equation and I'm plugging it in for both of them. Okay. And so this is equal to mass of the object over mass of water times the volume of water over the volume of the object. Okay. And so if our object is floating because its density is less than that of water, then what that means is that the entire mass of the object is supported by the buoyant force. And what that means is that according to Archimedes' principle, which says that the upward force that an object feels is equal to the weight of the water displaced, what that means is that the mass of the object is actually equal to the mass of the water. And so we're left with just V water over V object, and V water is the volume of water that was displaced. So this is equal to V displaced over the volume of the object. And this actually isn't even equal to a percentage. This is a ratio, but if you multiply this times 100%, you get the percentage of the object submerged. Okay? And so that's sort of where you get that from. And then for part 2, you actually did an experiment with these 6 objects, right? And so, you put them in water, you looked at what was different from them, you looked at the tension essentially, but you were really trying to answer these questions here. So 2.2.1 is like, which properties of the object does the buoyant force depend on? It depending on how you interpret the question, you can answer it differently. The truth is that the buoyant force only depends on the volume of water that you've displaced. So I guess in some ways it is only dependent on the volume of the object, but obviously if you have a really dense object, then it will only displace as much water as the volume of the object. However, if you have a very light object, then it may only displace like 0.2 of the volume of the object because the object's floating. So the answer here is like kind of volume, but I think the important thing is to understand that buoyancy only really depends on how much water you're displacing. And then which properties of the water matter for determining the buoyant force? Really only density. You can't experimentally show this because we can't really change the properties of the water, but it's going to be density. And then, and obviously, I guess if you consider volume a property of the water, then that certainly matters, because if you don't have enough volume of water to for an object to displace, then obviously you can't maximize the buoyancy force. But I don't really consider volume a property of water. I consider like density would be a property of water. So do any of the dependencies change when they're partially or fully submerged? No. I mean, density still matters, right? So 2.2.2 is definitely the same. And for 2.2.1, we still only really care about the volume of the water that's been displaced. So obviously the buoyancy force will be less if you submerge less, but overall it's still dependent on the volume of water that you've displaced. And then which property can be compared between the water and the object to determine whether the object will float? Again, it's density. So this is actually definitely all that matters, because if you put an object with, a lower density than water, it will float. If you put an object with a higher density than water, it will sink. And if you put an object with the same density as water, then it'll be what's called neutrally buoyant, meaning it doesn't really sink or float. It's just like you can place it anywhere in the water and it just stays there. So there's no net force. And then, 2.3, you wrote the procedure. There's a ton of different procedures you could have written. But you all wrote a good procedure, so that's good. You really just want a procedure that measures the buoyancy force or the tension, which you can use to calculate the buoyancy force for all 6 objects, and you want to do that outside of the water, half submerged in the water or partially submerged, and fully submerged. And if you do that, you'll have 6 times 3 equals 18 measurements total. And from that, you can get all the data you could possibly, or you can make the conclusions you want to answer these questions. Okay. And so then the thought experiments. Let's assume there's a massive volume of water that's in a transparent aluminum box, and it's in free space, and there's no gravity and no air bubbles. Okay. The no gravity part's very important. You're gonna draw the forces acting on the ball and then see if they're different. Okay, so for this ball in A, if there's no gravity, that means that there is no mg force, right? That's not a thing. And if there's no gravity, then that means, if we remember back to the beginning of this video, when I said that the difference in the buoyancy force comes from a difference in pressure between 2 levels of water, and that difference in pressure comes from gravity pushing down on the water above some given layer of water. So as you go deeper in water, the pressure increases, but that's only because of gravity. So if I have no gravitational force acting on the ball, and I have no difference in pressure because there's no difference, because there's no gravity pushing down on the water, then that means that there is no net force on this ball. Like, you may have pressure on all sides still, but there's no difference in pressure, which means that the ball stays still. And in B, we have the same case. It doesn't matter if I put it in the bottom right corner. It's still the same thing. There's still no difference in pressure, and therefore the net force must be 0 in both cases. Yeah, that's pretty much it. So the forces are not different. They're the same. Okay? And so in 3.2, you're looking at a meteorite in water. So draw a force diagram for the meteorite when it's being weighed underwater. So our meteorite, it's in water. It's going to feel some normal force from the scale. It's going to feel some buoyancy force, or not some buoyancy, it's going to feel a gravitational force down, and it's also going to experience a buoyancy force, okay? And then using your force diagram, find the volume of the meteorite in meters cubed. So in order to do this, we need to know what the buoyant force is, okay? So the normal force we know is 96. And we know that if we add the buoyancy force and we subtract the mg, which is 153, we should get 0 because everything's balanced. So then we find that the buoyancy force is 153. Actually, you might not be able to see the left side, sorry. Let me redraw it so you can see what I'm writing. Okay. So let me redraw my free body diagram as well. Okay, so the free body diagram, we have a buoyancy force up, right? and then we had a normal force due to the scale, and then we had mg down. Okay, and so now I'm going to draw it over here. Okay, so we know that we know if we add the three forces together, we should get 0 because our object is no longer accelerating. Right, and we know the normal force is 96, the buoyancy force we're looking for, and then we know mg is 153, and this means that the buoyancy force is 153 minus 96 equals 57. Okay, and so it's equal to 57 and newtons specifically, right? And we need to find the volume of water from that. Well, the nice thing is we know that the buoyancy force is also equal to rho g v. Okay, and this v is what we're looking for. So the density of water is 1,000 kilograms per meters cubed. G is 9.8 1 meter or 9.8 meters per second squared, and then that means that v is 57 over 1,000 times 9.8. Okay. And so 57 over 1,000 times 98 is equal to 0.0058 meters cubed of water has been displaced. Okay. And then let's move back up over here. So if our volume is that, I think that actually answers 3.2, right? So we found the volume of the meteorite, but now we need to find the density of the meteorite. So the volume of the water displaced is, I guess what we found here is the volume of the water displaced. But what I'm saying is that the volume of the water displaced is equal to the volume of the meteorite, because you can only displace as much water as your volume. Okay? And so what that means is that the volume of the meteorite is 0.0058 meters cubed. But now we need to find the density of the meteorite. So density is just mass divided by volume. We don't know the mass of the meteorite, right? But we know the weight is 153, and weight is equal to mg, right? Which means the mass is 153 over 9.8, which is equal to 15.61 kilograms. And now I don't have the right number of sig figs, but that's not super important here. So, and this means that the density is 15.61 over 0.0058, and that's equal to 2,684.21. Okay. Let me just double check that. I guess if you divide it like how I've written, it would be 2,691.38. But if you use the more exact values, you'll get 2,684. Okay, and we can see this is equal to 2.7 times 10 to the third kilograms per meters cubed. And we can see that matches aluminum at the top. And so the other part of 3.2.3 was like, what material is this made out of? Okay, so it'd be aluminum. And then 3.3 is, now imagine you were to dump the iron off the side of the boat. I don't know what de-iron they're talking about, but just imagine you have a boat and you have, like, I guess, yeah, imagine you have a boat and then you have iron on it and then you dump the iron off. The question is the amount of water displaced greater when the iron's on the boat, or is the amount of water displaced greater when the iron is off the boat? Meaning I just threw the iron into the water. Okay, so the answer here is that the amount of water displaced is greater when it's on the boat, because when the object is on the boat, let's assume the boat is like pretty light relative to the object, although it doesn't matter. I think it's just easier to think about if you think about it being light relative to the object. But either way, you get the same answer. So if the boat is light relative to the object, what we're essentially doing is we're giving the object like an equivalently lesser density than it actually has. So essentially, we have this object with like a high mass, but also a really big volume. And so it's able to displace a lot of water. Okay? But in the second case, the boat, since the boat's pretty light, it doesn't really displace a ton of water because if the boat's light, then the amount of water it's displacing is just equal to the weight of the boat. Like the weight of the water it's displaced is equal to the weight of the boat. And if the weight of the boat's small, then the weight of the water displaced is small, and therefore the volume is small. And the object, even though it's super heavy, it has a pretty small volume. And again, we can only displace as much volume of water as our volume, or the volume of the object in the water. And so what that means is that the boat doesn't really displace much volume itself, and the object doesn't really displace much volume itself, because even though it's really heavy and it wants to, it doesn't have enough volume to displace a lot. But in this case, we have a large volume. We have a large volume of water being displaced because this heavy object has like an equivalently large volume now because we put it on the boat. And so this boat is going to like sink down significantly. And so you'll end up having a boat that's much more sunken to the water than in this case. All right. And so that's the end of lab 1. Hope some of that made sense. Let me know if you have any questions.